Welcome back to Chapter 14 and 15. We're on to Part 3 now for Introduction to Inference. Last time we said that we could have the sample mean in between the population mean minus 1.96 times sigma over the square root of n, and between the population mean plus 1.96 sigma divided by the square root of n, that sample mean would be within those bounds of the population mean 95% of the time. And we said, well, if that's true, since mu and x bar, sampling distribution of the sample mean, that the mean of that distribution equals the mean of the population, then we can flip this to put mu in place of x bar and x bar in place of mu. So we get that the population mean is within x bar minus 1.96 sigma over the square root of n and x bar plus 1.96 sigma over the square root of n. And what did that give us? We thus can have 95% confidence interval for the population mean based on a sample mean. We could take the sample mean plus or minus 1.96 sigma over the square root of n. What this means, if I take samples of a certain size and I calculate the sample mean, and for each of those sample means I create an interval like this, where the lower end point is x, the mean that I just found, minus 1.96 times sigma over the square root of n, and the upper end point for the interval being x bar plus this product, 1.96 times sigma over the square root of n. If I kept getting intervals, I kept taking samples and making these intervals over and over and over again, about 95% of those intervals truly will contain the population mean. And what we see here is, it's a form of the point estimate. Our point estimate here is just our statistic, x bar, and the margin of error. The margin of error is always your critical value times the standard error. And the critical value is based on what confidence level you would like to have. So the margin of error here is 1.96 sigma times sigma over the square root of n, because we wanted a 95% confidence interval. Now a question: what is the proportion of time the confidence interval contains the sample mean? And you see the answer, it's 100% of the time, because look how the interval was made. You use the sample mean to make it. So these confidence intervals are about estimating the population mean. We use the sample mean plus or minus a margin of error to create intervals that we hope will contain the mean. And in fact, if we do the procedure over and over and over again, 95% of the intervals we produce will truly contain the population mean. Now, there can be many other levels of confidence, but the three that we're going to focus on, especially for quizzes and your tests, will be what you're going to see on this slide here. If we want to compute a 90% confidence interval or a 99% confidence interval, we would just need to find the right standard normal value. In general, for a 1 minus alpha times 100% confidence interval, we need to find the right critical value. That is the z-score such that the area to the right of it is alpha divided by 2. So here are the frequently used levels of confidence and their related critical values. For the 90% corresponds to z alpha over 2, the critical value being 1.645. For a 95% confidence interval, which we just did, it's 1.96. And for the 99% confidence interval, using your standard normal table, it's 2.575. We're going to learn later that there's a more accurate number for that. But for right now, this would be the best that we could do. So where do these values come from? Let's explore this. This goes back to techniques that we were doing in Chapter 3. So how do we get these numbers, like I said? Well, let's look at the 90% confidence interval. So when we want to find a 90% confidence interval, we're talking about having a confidence level of 90% or 0.9. So we have this significance level, we call it alpha. Alpha will always equal 1 minus the confidence level. So in this case, with the 90% confidence interval, where our confidence level is 0.9, alpha can be determined by 1 minus 0.9 or 0.1. So our significance level is 0.1. So we need to look for z-values such that 90% of values is between those critical values that we're going to find, or 10% equally distributed at the right and left tail end. That is, to find 0.05 to the left of a z-value and 0.05 to the right of that z-value that we're going to find. Now, something that we didn't get heavy into is the notation. When you have z, a little z, and it's subscripted by a proportion, what that means is, like this z alpha over 2, so in our case it would be z 0.05. What that means is find the z value such that 0.05% of the values, 0.05% of data values will lie to the right of it. That's what that always means. It's the probability z is greater than z, and whatever that subscript is, that probability equals whatever the subscript is. So that's notation. Again, didn't get real heavy into it. Still won't get real heavy into it. It's not like you have to know this notation. But if you should go further along in statistics or take another statistics course, more than likely you'll see that notation. So in this particular case, for a 90% confidence interval, we need to find what z-value such that 5% lies to the right of it. Because if 90% is in between the z-values, then you have to equally distribute the 10% to the right and the left tail end. So you divide the 10% by 2, or give 5%, and 5% is 0.05. So you would look on your z-table to find out what the z-values would be, such that to the right or to the left of that z-value is 0.05, and you get negative 1.64 and negative 1.65 being equally distance from from the probability of 0.05. So we did the add them and divide by 2, just like we did in chapter 3 and in chapter 11. So that's how you find the 0.05. So if you remember, go back to chapter 3 to remember how to do those. If in the chart you can't find the z-value closest to the probability you're looking for, if both probabilities are equidistant, then you just take the average of the two. So let's look at the 95% confidence interval. How do we get the critical value? Again, our confidence level is 95 or 0.95. To get our significance level, alpha, it's 1 minus 0.95, and in this case that would give us a significance level of 0.05. What that means is we need to find the z-value such that 95% of the data values would be in between those two z-values, or we have to divide the 5% equally among the right and left tail end. So what we mean by that is that 0.025 or 2.5% of the data lies to the left of the z-value, and 2.5% of the data value lies to the right of it. So you'd look into your z-chart, you look for 0.0250, and you would find that we hit it right on the nose, that negative 1.96, the probability that z is less than negative 1.96 actually equals 0.025. So we found our z-values, negative and positive, and those are our critical values that we're going to be using in here for a 95% confidence interval. Now the critical value is classically, the critical value is your z that's subscripted alpha over 2. So it will always be a positive number, so the critical value for the 95% confidence interval is 1.96. For the 90% confidence interval, the critical value is 1.645. So for the 99% confidence interval following the same procedure, the critical value is going to be 2.575. And we'll know how to construct these different confidence intervals for these different confidence levels. And in the next installment, we'll see how that works.